All right. Hi, everyone. I'm Josh Karpel, machine learning at Workday, and I'm going to be talking today about how you, too, can save 50x on your model serving costs using reserve. So a little bit about Workday. Workday is the AI platform for... how's my audio? Good? OK. Workday is the AI platform for people, money, and agents, software as a service company for HR and financials. Our customers are things like companies, hospitals, universities, not individual people, right? It's business to business. And those companies purchase features from Workday a la carte, right? And that makes sense for them because we have lots of different features and we have lots of different kinds of companies, so they want to customize. And a lot of those features are, of course, powered by AI. And in our particular context, we use a lot of tenanted models. And the reason for that is that we have thousands of customers all around the world, and they have very different scales. They have very different kinds of businesses, right? There's huge differences between a small hospital and a large company and a university or something like that. And they all have these different features enabled. And what that means is that a lot of our AI features, to achieve the kind of accuracy that we actually need to help our customers, use a mix of global and tenanted models. Tenanted meaning that that model is created solely for that customer using solely that customer's data. We don't cross-pollinate them at all. So the question that then arises, and is the subject of this talk, is how can we serve all of these models cost effectively, right? Because we're going to have thousands of customers, each with models for a variety of features. That's thousands, tens of thousands of models. So for a long time, we used a system called tenant sharding to solve this problem. And the way that tenant sharding worked is that users of our platform would write applications, like Python applications, that load and execute models and the business logic of their application simultaneously. Then we have this system called the tenant sharding controller. And its job is that it actually clones the Kubernetes deployments that those services create as part of their Helm charts. And those clones we call them shards. And the idea is that the tenant sharding controller configures each shard to load a bin-packed subset of all the tenanted models onto that application. So each of the sharded pods loads all of the global models that are needed for that business use case that it's solving, plus all of the assigned subset of tenanted models configured by the sharding controller. And then the sharding controller also does some routing information on top using Istio virtual services to make sure that requests actually get routed to the correct deployment. If you're interested in more details on exactly how this tenant sharding system worked, we actually have a blog post up on the Workday engineering blog that you can take a look at for more details. But this system has a couple of problems. The biggest one is that every pod in every shard loads all of the global models, which means you end up with way too many replicas of all of the global models. And that's because all the processing is done locally in each application, right? Also, there was no support for horizontal autoscaling in this system. So every shard has the same number of replicas, regardless of how busy that shard actually is, which means that the scaling of every customer's model is coupled to every other customer's model. If they're in the same shard, or because we don't have horizontal autoscaling, if you're in any shard, every model is going to have as many replicas as we need to serve the largest customers. And as I just said, right, one of the key points of our business is that we serve customers of all kinds of different sizes. So unfortunately, that means we have to have as many replicas as we need for our largest customers for every customer. And then that number of shards times that number of replicas of all the global models, which is a lot. Also, the system could only shard on one model at a time. And that meant we were running into sort of conceptual architectural problems about how we were going to do things like blue-green migrations if you're changing the schema version of your model or something. Or if you wanted to do an A/B test experiment, we were looking at problems that we were going to have to work around where we would have to build B models for every tenant, even if that tenant was not participating in the B experiment, just to make the internals of the system work. And we didn't really like that. So around 2023, we decided to build a new solution to this problem using reserve to try to kill a lot of birds with one stone. And the way that our new system works with reserve is that we have sort of isolated the model serving onto a single application, and then the business logic applications call that application. So it's sort of like an internal serverless platform. And the idea is that inside of our array cluster, there is going to be a model controller, which is reconciling continuously between our model registry, which has all the information about which models we want to load and how to load them, with the serve controller. So it's actually going to create a serve application with a single deployment in it for every model you want to run. And in addition to that model controller application, we also have an ingress application. And the ingress application's job is to do all of the shared stuff that is not actually executing the model bytes on data, right? So it handles like the public HTTP API, it handles authentication and authorization, it handles rate limiting, et cetera, et cetera, et cetera. And just sort of by virtue of using Ray Serve, right, those are all separate Ray applications, and they all autoscale. The deployments inside them all autoscale independently. And that's where we got the 50x cost reduction, right? It just sort of falls out naturally of using Ray Serve. Now, it helped that we started with way too many replicas. That's how we get such an amazing number like 50x. But that's, I mean, you know, I could kind of end the talk right there, right? That's it. That's where we got the cost reduction from. But it goes beyond that, right? Because now we can do things like deploy different model versions or A/B test experiments, things like that, at roughly linear cost, right? So in this system, if you want to add a new model to the system, you just add that new model with whatever your minimum chosen number of replicas is, like 3 for fault tolerance or something. So that happens at like roughly linear cost instead of having to do things like clone the entire deployment and stand up new copies of replicas of global models that, say, aren't under the experiment. Now, you may have realized that this is sort of not what you would get out of Ray Serve if you like go read the Ray Serve documentation. So if you read the Ray Serve documentation, what you're going to find is that the tutorials are all going to look something like this. You have a few applications, and each of those applications is going to have a few deployments in it. And you're going to write them all out by hand statically in your serve config.yaml file. If you're using Ray, then maybe that it goes in the serve config, CRD, et cetera. So you're going to end up with sort of like a handful of applications per Ray cluster, each with a couple of deployments inside them, possibly a lot of replicas, but not a very complex like actual set of applications and deployments. Our usage looks very different from that. Our serve config has exactly 2 things in it, and neither of them are models. One of them is the model controller, which is responsible for that reconciliation loop. And the other is the ingress application, which might have a lot of replicas, but doesn't actually do any model processing itself. All of the models are created dynamically at runtime by calling serve.run and serve.delete. And there's going to be thousands of them, and each of them is going to have a single deployment in it, potentially with many replicas, but a lot of them are going to have very few replicas. And this went totally fine. Everything was fine. Nothing went wrong when we tried to actually deploy this system. No, of course things went wrong, because this is not quite what the serve team was expecting people to do, I think. So we ran into some problems. But to describe those problems, I need to talk a little bit about how serve works under the hood. And I think it's this is like not information you really need to know to like operate Ray Serve at your company. But this is the kind of information that you might be interested in if you've been having problems with Ray Serve that you don't know how to explain. And what's so cool about Ray Serve, and really the real reason to learn this, I think, is that it's open source. It's written in Python. It's written in remarkably readable Ray core, right? Like it uses the same Ray core API that we know and love from using Ray core. So you too can go read it and, as we will see, improve it. So let's talk a little bit about the internals of Ray Serve. All the boxes on these 2 sides are identical. What's different is the arrows. But the thing that's the same on both sides is the client request flow, which is in green, right? So a client is going to send a request to your Ray cluster. And it turns out that there's a component running on each Ray worker called the serve proxy. And it's the serve proxy's job to actually accept that HTTP or gRPC request. And then what it's going to do is use a part of Ray Serve called a deployment handle, or just handle, to route that request down into the application that is actually specified by your like route prefix. Now, I've diagrammed our system here, and in our system, we only have one ingress, and it's mounted at /, right? So all the requests are going to hit the serve proxy and then go down to our ingresses. If you have lots of different route prefixes in your system, the serve proxy would be the part that's responsible for routing them down, and there's a handle for each of those routes. Then again, in our system, those ingress replicas are going to have handles to all the model deployments, and they're going to use that handle, just like the serve proxy did, to send the request down into one of the actual model deployment replicas. So this is the part of serve that you use either explicitly or implicitly, right? So if you're going around typing like deployment.bind and stuff like that, or setting route prefixes, this is all happening transparently for you. There's handles getting created in the background to make that information flow. But to actually make this work, serve is doing a lot of work in the background to shuttle information around the system that's needed for these things to work. In particular, on the left, we've got the request routing metadata flow. So I just said that these handles are responsible for actually routing the request. And what that means is that they need to know where the replicas of the deployment that they are routing to are in your array cluster. But they don't have that information, right? Because that information is held by the serve controller running on your head pod. So they actually ask. The handles are in the background continuously asking the serve controller, where are the replicas of the deployment that I am pointing to? And then when a request actually comes in, the handle knows where to send those requests to. So here you can see that these orange arrows are on the left are requests from the handles to the serve controller asking where those replicas are. The blue checks coming out of the controller are health checks. That's the controller checking that the replicas are still alive, because we don't want to route requests to dead replicas. On the right is the autoscaling metrics flow. So you may know, as we just said, that reserve has autoscaling as like to me, the big feature, right? That's how we got our big cost reduction. But to actually make that work, the system has to know, the serve controller has to know how many requests are actually flowing through the system to all these components. And so that information is getting sent from every replica. In our case, that means both ingresses and model deployment replicas, but also each handle. So it's actually recording information on both sides. The replicas are recording how many requests they've processed, and the handles are recording how many requests they have sent to each replica. I think, actually, I might be a little outdated on this because things have been changing upstream in Ray on this. I think there's even like more information that gets propagated in that flow these days. But the arrows are correct. I think there's just even more information that's carried there. So let's try to estimate how much work those two information flows have to do in the background. So our system fell over when we had about 10 ingress replicas and 100 models, which means 100 serve applications, each with one deployment in them. But that deployment had 3 replicas. So that means we have 10 ingress replicas and 300 model replicas. And that means that each of our ingress replicas, which need to each be able to route to any of the model replicas, need to have 1,000, we need 100 handles each, which is 1,000 handles. Each handle pulls the controller for routing data every 30 seconds. It's like not quite a pull. It's more efficient than I'm making it sound. If someone wants to ask about that in Q&A, I can elaborate. And then also, each handle and replica is pushing autoscaling metrics to the controller every 10 seconds. So if you add that up, you get about 30 requests per second of routing metadata and 130 requests per second of autoscaling metrics. And the thing is that that is happening all the time, regardless of whether there are actually any client requests flowing through the system at all. So what we did is that we set up our system like this, and it fell over, even though there was no traffic coming in, which freaked us out. And so we tried to figure out what was happening. And it turns out that what we had done was essentially overload the serve controller. So the serve controller has a pretty typical control loop structure. There's a big while true loop. And then inside that loop, there's sort of 2 phases of things that you do. The first phase is that you do your controller stuff. These are like the actual reconciliation actions that the controller is going to take. So in the case of reserve, that's things like checking on replica health, right? So that it knows which replicas are healthy so that it can tell people to route to them. And it's also doing things like making and acting on autoscaling decisions, right? So it's having all this autoscaling information sent to it, but at some point it has to actually process that information and make autoscaling decisions, and then use the Ray Core API to like go make or destroy actors. And then there's phase 2. And in phase 2, we stop doing controller stuff and we sleep. And it turns out that the serve controller is actually, it literally is an async Ray actor, right? It is literally implemented that way. And so what that means is that while this background task is running, this sleep is the only time that that actor can respond to incoming requests. And those requests are all the things we just talked about. So there's the routing metadata requests, there's the autoscaling metrics being pushed to it, and, very importantly, health checks from KubeRay, right? So if KubeRay doesn't receive a positive health check from the serve controller when it asks, it is eventually going to decide that the cluster is unhealthy. And what happened to us is that we broke a pretty fundamental assumption here, which is that the assumption when writing a loop like this is that do controller stuff is really fast, that it's much faster than how long you sleep for. So by default, reserve control loop interval seconds is 100 milliseconds. And do controller stuff probably takes like order a couple milliseconds, right? So what that means is that because that sleep is fixed, and because do controller stuff is small, you spend a large fraction of every second or every minute or whatever sleeping. And when this is sleeping, it's responding to all those requests that it needs to respond to. But if you give the controller lots of stuff to do, like say you give it a second worth of work or 10 seconds worth of work to do, then the fraction of time that it spends sleeping drops by a lot. And if you don't have enough time during that sleep to process all of the requests that have queued up from routing metadata, autoscaling metrics pushing, if you don't give it enough time to respond to all of those during that sleep interval, they're going to queue up forever, basically. And at that point, one of two bad things will happen. Either you will miss enough health checks from Kubray that Kubray decides that the cluster is restarts it, are going to build up so many requests that you actually go out of memory. We're good. Oh, hello. Oh, now it's working again. See, as soon as you started walking toward me, it started working again. So, oh, but then it stopped working. So yeah, probably. By this interval gets too low, then the controller is going to fall over. So we panicked, and we did a quick fix. And the quick fix is that we made it so that this sleep interval is actually configurable. Previously, it wasn't. It was fixed to 100 milliseconds, but we did a quick upstream PR to make it so that you could actually configure this. And, all right, now I got to use this thing. Hello. Check, check. Hello. So we did a quick upstream PR to make sure that we could actually configure this thing. And that's a great Band-Aid because what we can do is that we know how long do controller stuff lasts. So we can just increase that sleep interval until the system stabilizes again. So that worked, and it let us get our first like 100 models out. But we knew that was not going to be sufficient because, as I said at the start, we have many thousands of customers, and we have lots of use cases that use AI. So we're looking at wanting to host thousands, tens of thousands of models per region. So we knew that this was not going to be sufficient. We knew that we needed to make architectural changes to how Serve worked to make our use case work as we wanted it to. So we did two big fixes that I'm going to talk about briefly here, and they're both sort of the same flavor, which is that they are about doing an amortization process. So amortization is just the idea that you're going to take something that you were previously doing in lots of little chunks, and you're instead going to do all of that work in one big chunk. And the only reason that you would expect this to change the efficiency of the thing you're doing is if there's a lot of overhead every time that you actually initiate this action. Now, in this case, we have good reason to believe that because there's a lot of overhead in actually making this RPC request, right? We know that the network is slow compared to memory, right? And especially compared to the CPU. So the theory was if we can amortize the two data flows that I talked about earlier, then we should be able to see a performance improvement. And in fact, that's what we did. So the first one that we did internally is that we built a fork of Ray. And in that fork, we introduced this component called the shared metrics pusher that sits in between the handles and the serve controller. So each Python process gets its own shared metrics pusher for all of the handles that are in that process. And that shared metrics pusher gathers the autoscaling metrics from all the handles and then pushes them in one go to the serve controller. So instead of having, say, 100 handles individually pushing metrics in like a background loop, you have one metrics pusher that pushes all 100 in one go. Now, again, how much this is going to help depends on the overhead. In practice, what we saw is that the CPU usage of the serve controller when you make this change went from more than 100%, i.e. it didn't have enough time to do all the work that we were asking it to do, went down to 0% after we made this change. Now, embarrassingly, this PR is actually not yet merged upstream. It was the very first thing we did, but it is going to be the last of these changes that we actually managed to get merged upstream. I can talk about why if someone's interested. Okay, so big fix number two, same idea. We're going to amortize something. In this case, it's the other information flow. It's the routing metadata. So in this case, we basically just reverse the arrows. So the system that does this is called the long pole client. And so we introduce a shared long pole client. And its job, just like with the shared metrics pushing, is that the shared long pole client knows all of the handles that exist in this Python process, and it's going to get all the routing metadata that it needs from the serve controller for all those handles in a single shot. Again, the only reason that you would believe that this would cause a dramatic improvement is if there's a lot of overhead. It turns out there is indeed a lot of overhead. You make this change, and the CPU usage drops even more. This one has actually been merged upstream for quite a while now. You're all benefiting from this if you're using RayServe. Plus, we did a lot of other small contributions. So a lot of this stuff is like basic data structures and algorithms type stuff. It's stuff that looks like completely fine code in the serve controller if you think that you're only ever going to have like 10 applications. But if you have 1,000 applications, this stuff starts to fall over. So it's things like making sure we're using dictionaries to do lookups instead of searching through lists, things like that, things that you would never expect to be a problem unless someone uses your system in a slightly odd way, which is what we do. There's also, I would be remiss to mention that there's one big one here, which is the one at the top, which is that we wrote a blog on solving some interesting problems we had with making sure that Ray and Istio play nice with each other. The way that Ray handles ports and the way that Istio thinks about ports are kind of weird. So if you're having problems getting Ray and Istio working together, take a look at that blog post. And we reprofile the serve controller pretty regularly, right? Because as we keep on scaling, we keep on making it do more work. So we're always coming up with these little fixes. You know, whatever the most expensive thing the serve controller is doing is on any given whenever, we try to knock it down. But none of this would have been possible without support from the RayServe team. And I think they did a really amazing job helping us out here. So the first is that when we were just starting out and we didn't really know enough about the internals of RayServe, we didn't know the stuff all of the stuff I just described. They helped us out by just straight up doing some of the fixes that helps us out here. But more than that, they were super open to contributions, suggestions, discussion on Slack, on GitHub. And that's just, I mean, I think that's one of the superpowers of the Ray project is that it is open source, right? So like you can go read the code, you can suggest you can ask a question, you can make an issue, you can make a contribution, get it reviewed by the team that built the thing, and make a contribution that's going to help a lot of other people. And it's not just that it's open source, it's that RayServe builds on the primitives of Ray core, right? Ray is built on top of itself. So if you know Ray core, you can go read the RayServe source code. It is remarkably understandable. And then you can make improvements to it. So by our powers combined, you can now run thousands of serve applications in a single Ray cluster, tens of thousands of total replicas. You can have hundreds of ingresses with handles to every single one of those applications. So it's like hundreds of thousands of deployment handles in your cluster, orders of magnitude higher than when we started on both counts. And the result of that is that Workday is self-hosting more models than ever before, and we're doing it on the cheap. So huge thanks to the AnyScale Serve team. I listed a couple names of people that we worked with there. And also, of course, big thanks to my team at Workday that works on all this stuff. All right, with that, I'll thank everyone for coming. You can follow up with me right now. I think, do we have time for Q&A? Yes, we have a little bit of time for Q&A. And then I'll also be at the conference along with my colleague, Jugal Shah. And you can also hit us up on Slack. Thank you very much. All right, I think if you have a question, I believe there is going to be a microphone floating around, but I cannot see anything through the spotlights. So I hope something's happening out there. No questions?
Well,
oh, here we go.
Here. Why was the handle sending metrics to the serving?
So the question is like, why does the handle send autoscaling metrics?
Apart from just the pod itself, like what was the extra thing? Was it like just to scale the handle itself separately in the same pod?
No, so the handles don't autoscale themselves, right? They're kind of designed to be, they don't have like an autoscaling component themselves. I don't 100% know, actually. I think that part of the reason is that you get the information sooner if you record it on the handle, right? So if you're recording metrics on the replicas that you're sending the requests to, you get the request, and then at some point you finish the request, right? And at that point, you kind of like know that you've processed the request, and you can send the autoscaling metrics. If the request is going to take, I don't know, a minute to process or something, right? You can get the some information much faster if you know how many requests the handle has sent to each replica. right? So I don't know exactly how they mix these in the serve controller to arrive at the final autoscaling numbers. I think also some of this code is changing right now because I don't remember if they mentioned it in the keynote or not, but there's been a lot of work in reserve around like custom autoscaling metrics. So that's what I was referring to earlier, that there's like actually a lot more information that flows through those channels now. And I don't know if all that information can be collected like purely on the replicas or if some of it needs to be collected on the handles or something like that.
A follow-up question to that is, when you amortize the requests, were you, was the chief amount of time, because you were sending in so many requests, was it spent on like opening and closing connection pools?
Yeah, so the connection pool stuff would be on the handle side. This does actually, I mostly was talking in the talk about like the serve controller performance, but it does actually also help for us on the ingress side too, right? So we have lots and lots of handles that all had these background tasks, and now there's only one. So I don't know that it helps on like a connection pooling thing, because I think they were probably all sharing a connection pool anyway. But what it does help on is like serialization cost and like having so many little background tasks running. And it also helps with things like actually the machinery of initiating the like gRPC connections internally in Ray or whatever, right? So there's a lot of overhead that goes into each of those connections that you can amortize.
Okay, thank you.
All right, any more questions? Okay.
Hi, thank you for the great talk. And can you tell us the story on why your first PR hasn't merged yet?
So here's the trick, right? So the reason that this one was easy. And the reason this one was easy is that as a user, you actually don't have any control over the system. So there's nothing user configurable about this. It's happening in the background all the time. And there's no like configuration options you can put anywhere that affect how this works. I guess there might be like global environment variables, but they were already like that. This one, unfortunately, has a user configurable option that is configured at the deployment level. So it turns out that on your deployment handle, one of the autoscaling options is like metric interval seconds. That is the push interval for the autoscaling metrics. And you can set a different one for different deployments. So we had to deprecate that because now it's controlled. It's the shared metrics pusher is the thing that controls the push interval, and it's a single global environment variable. What has already been merged is a PR that deprecates that individual granular setting on the deployment handles. We have to let that go for a few releases before we can merge the next PR. But then also the problem is that trying to get the tests to pass under this PR is a little tricky because there were lots of tests that override the metric interval to make it really short in the Ray test suite to make autoscaling happen really fast so that the test suite runs quickly. So I have to go find all the places where they did that and make sure that we're instead using the environment variable to change it. And then it's tricky because it's an environment variable, so it's only on process startup, et cetera, et cetera. So it's been a little trickier to get this one merged.
We have time for one more question. So,
thank you so much for the question. So, from an uneducated point of view, I listen to this talk and I see a huge risk, right? So the topic is, can we host 10,000 models on Ray Serve? And the PR to make it happen hasn't merged yet, right? So, is the answer no today?
Yeah, I guess. So it's not internally, right? Because what we do is we do this internally, right? We have a fork where we've made this change. So yeah, you can't. I would say you can't quite do this on open source Ray today. Coming soon, I guess, would be the answer there. But you can certainly do, I think, probably like hundreds or thousands without this. It also kind of depends on how many. It depends a lot on how you're using handles, right? So actually, it turns out that in our system, the problem was mostly the handles, not the replicas, right? So like if you had lots of deployments, but you were just routing to them with route prefixes and you didn't have extra handles being created, you might be okay. That's the kind of thing I would say, do at your own risk.
right.
Until this PR merges, then it'll be great.
Okay, thank you, Josh.
Yeah, thank you.